Okay, well, the circular model is just, you have a circle of radius A to model an A cosine of omega t plus phi. Whether that is a charge function or a position function or some other function doesn't matter. Now, phi is our initial position. When t equals 0, we have A cosine of phi. Now, if you understand the circular model and the trigonometric functions, you see that if phi is, if this is your angle phi, then this position is where you start on the reference circle at t equals 0. And correspondingly, you project down to the x-axis, and that's going to be where this model starts, because this model is A times the cosine of omega t plus phi. And if you understand the circular model, you understand that this is A times the cosine of whatever this angular position is. Okay, now if we got an angular velocity omega, counterclockwise angular velocity omega, then omega t is the angle through which we travel after t equals 0. We add that angle to phi, and that tells us where we are in the unit circle. And the greater omega, the faster we move around the unit circle. And the point down here in the x-axis just follows our unit circle position, just stays underneath the unit circle position, going back and forth, faster if you have a large omega, more slowly if you have a small omega. The period is the time it takes to go around the circle. Okay, well, our angles are generally going to be measured in radians, so implicitly the circle is 2 pi radians, and we divide that by omega, which is a number of radians per second, and that is the unit of omega that comes out of the differential equation in either case. It's in radians per second, and you should be familiar with that from first semester, but you might have to refresh yourself. Okay, so the period is just how far you go divided by how fast you move. To get all the way around the circle, which completes one cycle, you got to go 2 pi radians to get back where you started from. And you divide that by how fast, how many radians you're moving through per second, or whatever the time unit is, and you get the period. And frequency is the reciprocal of the period. Okay, frequency is how many times you go around in a second. That's reciprocal of how long it takes you to go around, how many seconds it takes you to go around. So there's your frequency. So we have to understand all that, and we have to really understand that. We don't want to have to stop and think too much about what that means if we're trying to analyze an actual system. We don't want to keep stumbling over the meanings of these basic quantities. So that's pretty much what you need to do to understand the LC circuit. Okay? And we have other possible circuits. We can put a resistance in this circuit, and of course the resistance is going to dissipate energy, just like in a mechanical system, drag. You know, a pendulum moving through air, the air is going to exert drag on it. You're going to have some energy lost because the string keeps flexing. So, yeah, you have that. Anyhow, there's your equation, completely analogous to what you would have mx double prime plus a drag constant plus kx. If the drag constant is, if the drag coefficient is in units of force per unit of velocity, okay? Now, you have other possible drag coefficients, so not every situation with drag gives you that simple of an equation, but if you have a linear drag force, basically, linearly proportional to the velocity, then you have the complete analogy to this system. Now, differential equations, we talked about that. In physics, we didn't do drag, okay? But by understanding this, you can go back and easily understand drag if necessary. Now, this system had no resistor. Okay, well, we could leave out either a capacitor or an inductor from this circuit here. If we leave out the resistor, we get this. If we leave out the capacitor, we have just an inductor and a resistance, and that's the circuit with no capacitor. And then if we leave out the inductance, nothing, no coils or anything, nothing to produce a back EMF, then we just have these two terms and we have this. Okay? Now, I tell people before lab on Friday, you need to be sure you can solve any of these three equations. And we solved both of these at one point or another in class, so you've already seen these. This one, I don't think we have done in class, so you might have to do just a little work on that, but you just plug in a CE to the RT or a DE to the RT, because you don't want to confuse that C, and take what it gives you.